The Rígel Project aims to develop a 1 km apogee rocket with solid propulsion, double event recovery method, avionics with telemetry, and an active stability control system. The concept of operations takes into account all the phases since the team preparation at the operational base to ignition, propelled flight, coasting, decelerated fall, and final rocket recovery. The project management has been fully adapted from NASA's system engineering methodology, where the design basis comes from a set of needs, goals, objectives, and the associated requirements, moving to the development of alternative design solutions to meet such demands, and from the progress reviews and decision analysis, determining the final design that best meets our criteria. The project is currently in phase C of development, having already completed the theoretical design and now with the team developing some of the practical activities related to the construction and testing of the rocket. The risk analysis developed by the team consisted of a FMEA and hazard analysis associated with a risk assessment matrix, where each risk of component failure or hazardous event had its associated consequences established, determining which action should be taken by the team, considering the severity, the probability, and a risk matrix.
Hello, our propulsion subsystem is a solid engine which integrates an aluminum casing with a EPDM thermal blanket, bulkhead and nozzle made of steel, and the solid grain is composed of potassium nitrate and sorbitol. The geometries and essential operation data of the engine are described in the tables. To verify the mission efficiency, a mathematical model of flight dynamics was implemented. The result of a flight simulation are in the graphics. Around 10,000 simulations were performed using Monte Carlo analysis in order to describe the possible land positions with and without the operation of the recovery. To verify some components, computational simulations were performed. Here we have the structural and thermal analysis of the bulkhead and the aluminum casing. In the CFD simulation of the nose exhaustion, we can observe that it is optimized without showing over or under expansion effects. To finish, this is the list of the components along with the weights.
Regarding the recovery subsystem composed by a two-stage liberation event, this is a drug tube, the smaller parachute which will open shortly after the rocket's apogee. Circular shape with an area of 0.4 meters squared, it will steady the rocket's fall speed to 21 meters per second. As soon as the rocket reaches 480 meters AGL, the 2.8 meters squared cross-shaped main tube is ejected, reducing the final speed to 8.9 meters per second. Both parachutes use 8 suspension lines and one riser. Both ejections are made through the explosion of black powder, which separates each tube by breaking the nylon screw fuses. The system also counts with 5 bolt and swivel links as connective elements and a protective cover to prevent burn damage. Here we have some general data about the subsystem and complementary info about our components.
Our avionics subsystem features a wide list of equipment to offer our team a large number of futurely useful data. Along with the bioaltimeter, our microcontroller handles 2 altimeters and accelerometers, a GPS module, and a vibration sensor, all powered by a set of 3 encased 9-volt batteries plus a drone camera for live transmission powered by another set of 2 encased batteries. The avionics redundancy code operates on a starting phase that will set up the sensors and measure initial conditions, a loop that will make measurements and conditionally deploy the parachutes, and a post-landing stage that will turn on the sound beacon. Our team has run several analyses and has developed a circuit to securely house our equipment. In the following slides, you'll find relevant information such as our total weight of 720 grams.
The aerostructure is made of 5 pairs of couplers, 5 fuselage, a bulge tail, a nose cone, an aluminum tip, and 2 rail guides. The couplers will be made of 6351 T6 aluminum alloy and are designed to be fixed in the fuselage by epoxy adhesive and connected between them by screws. Our fuselage will have an inner diameter of 4 inches and 2 mm thickness and will be manufactured with fiberglass and epoxy resin. The following image is from a simulation that accounts the main parachute's infloat loads. This one is the low coupler receiving the max thrust from the motor. Here we can see some of the technical data of our subsystem. In total, the subsystem mass is 2.7 kilos.
The stability subsystem was developed and aimed to provide full control of the rocket's attitude during coast. The slide shows the avionics responsible for this task. In sequence, all the attitude control is going to be performed by 4 canard fins. Our rocket will also have 4 primary fins located over the motor's fuselage. Talking about our attitude control system, here we have the rocket flying model, including thrust, aerodynamic force and moments on the left, wind and atmospheric modeling on the right, and Newton-Euler equation solver on the center. For the controller, there is the sensors model on the left, the actuators model on the right, and the control arm on the center. Here we can see the model analysis of the primary fins used to obtain natural frequency, input to flutter analysis. This slide shows a little bit of our rocket flight performance. To finish, stability bill of materials. Thanks for watching.